Look at your phone screen right now. Every pixel you're seeing, your TV, white LED bulbs, bright streetlights, all of them quietly depend on one color that almost didn't exist. Blue. Red LEDs were invented in the 1960s, green in the 1970s, but blue? Blue stayed impossible until 1993. Not because nobody tried. Some of the biggest tech companies in the world threw unlimited money at this problem for decades. Blue wasn't hard. Blue was physically refusing to cooperate. And here's the weird part. When someone finally cracked it, he didn't even understand why it worked. He just tried something desperate, and it glowed. Here's what an LED actually is. It's a tiny sandwich. When electricity flows through it, the sandwich releases light, but the color doesn't come from dyeing the plastic blue or painting it. The color comes from an invisible energy drop happening inside the material. Think of it like dropping a ball downstairs. Drop it down a short step, soft thud, that's red light. Drop it down a medium step, sharper thud, that's green. Drop it down a tall step, loud crack, that's blue. Blue light demands the biggest energy drop, which means you need a material with a tall enough step. Only one material could pull it off. Gallium nitride, GaN on paper, could make blue. But in reality, two massive problems stood in the way, and both of them seemed impossible to fix. To build a bright LED, you need a perfect crystal. Perfect means atoms lined up in neat rows, like tiles on a floor. Early gallium nitride looked nothing like that. It was full of defects, atomic-level potholes scattered everywhere. When electricity flows through, it hits those potholes and gets trapped. The energy turns into heat, not light. So even though gallium nitride theoretically could make blue light, actual devices barely glowed at all. For years, this was the wall. Nobody could grow clean GaN crystals, until someone discovered a weird trick. Grow a thin starter layer first, basically a fake foundation, then build the real crystal on top of it. The starter layer smoothed everything out, made the crystal clean enough to actually try making LEDs. Problem 1 solved, but that just revealed problem 2. And problem 2 was worse. Remember, an LED isn't just one block of material, it's a sandwich. Two different sides pressed together. One side is loaded with extra electrons, imagine a crowd pushing forward. The other side is missing electrons, so it's pulling them in like a vacuum. When you connect power, both sides push toward each other, they meet in the middle. That meeting is where light happens. For gallium nitride, making the electron-rich side was easy. But making the other side, the electron vacuum side, completely impossible. Scientists knew exactly what ingredient to add: magnesium. They added it. The chemistry looked perfect. The math checked out. Nothing happened. LEDs stayed dark, year after year, lab after lab, failed attempts piling up everywhere. It was like following a perfect recipe, using fresh ingredients, setting the oven to the right temperature, and pulling out a cake that never rose. Not even a little. Everything was right. Nothing worked. So what was going wrong? A researcher named Shuji Nakamura was running out of ideas. He'd tried everything. Nothing worked. So he tried something that shouldn't have mattered. After growing the crystal, he hit it with a beam of high-energy electrons. Just blasted it. And suddenly, the LED lit up. Bright blue, real blue. The other side of the sandwich finally worked. Nakamura had no idea why. He later said he just tried it out of desperation, because everything else had failed. It took years for scientists to figure out what actually happened. Turns out the magnesium was inside the crystal the whole time, but tiny hydrogen atoms were blocking it. Keeping it inactive, the electron beam knocked those hydrogen atoms away, unlocked the magnesium. And once the magnesium was active, the missing electron side finally started working. The sandwich was complete. Blue LEDs became possible, but they still weren't bright enough to be useful. Even with both sides of the sandwich working, early blue LEDs were dim, because electrons from one side and the missing electron holes from the other side would just wander around randomly. Some would meet and make light, but most would just miss each other. So engineers added one more layer, a super thin zone in the middle, a trap. Think about it like this. If you want two people to bump into each other, where's it easier? In a massive football stadium or in a narrow hallway? This middle layer is the narrow hallway. It forces the electrons and holes to squeeze into the same tiny space. Now way more of them collide. More collisions means more light. Brighter, efficient blue LEDs. And that's when they became actual products you could buy. But the reason this mattered goes way beyond just making blue LEDs. Look at your screen again. Every single pixel is made of 3 tiny lights working together: red, green, and blue. No blue LED, no modern screens. Not your phone, not your TV, not the screen you're watching this on right now. And white LED light bulbs? Also impossible without blue, because white light isn't one color, it's a mix. The trick? Start with a bright blue LED. Coat it with a material that converts some of that blue into yellow. Your eyes mix the blue and yellow together and see white. Before blue LEDs, efficient white light meant either hot, power-hungry incandescent bulbs or those weird flickering fluorescent tubes. Now, white LEDs use 90% less energy than old bulbs and last 25 times longer. Streetlights, car headlights, every light in your house. This wasn't just one more color LED. Blue was the missing piece that unlocked modern lighting and every screen you've stared at for the last 20 years. That's why 3 researchers, including Nakamura, won the Nobel Prize in Physics for this in 2014. One of the most important inventions of the late 20th century, for a color you never even thought about. Blue is everywhere now. You just never thought to ask why it almost didn't exist. Have you ever wondered if Einstein had been wrong about time? Your phone's GPS would be wrong by 10 kilometers? If you want more questions nobody thinks to ask about the tech you use every day, hit subscribe.